All right, so now that we've seen how to do the technical bits of the Lagrange multipliers, now let's actually solve the example that was in the Mathematica video beforehand. Right? So in that video, we were looking at the situation where we're trying to extremize f of xy equals x squared plus 2y squared, subject to the constraint x squared plus y squared equals 1. Right? So we looked at the contour plot of f, then we drew in the constraint curve, and then we're looking for the places where the constraint curve is tangent to the level curves of f. All right, so now let's actually do the algebra for this and actually solve this and find the points and find the extreme values. Okay, so what that means is we have to set up the Lagrange multiplier system. So the first thing we need to do is find a function for the constraint, and that's not too bad. So the constraint, this is given by g of xy equals x squared plus y squared, and we set that equal to 1. Right? I mean, there's a whole number of constraint functions we could choose. We could say g is x squared plus y squared minus 1, and then g equals 0 is the constraint. You know, there's a whole bunch of choices here. Okay, so we'll use this one, though, because it's the easiest. All right, so now we need the gradients of f and g. So the gradient of f, well, that's just 2x, 4y. Right? And the gradient of g, well, that one's even easier, just 2x and 2y. Okay? So now what we need to do is set up the Lagrange multiplier system. So we'll do that over here on the side. Right? So we have 2x equals lambda times 2x. Right? We take the x component here and take lambda times the x component here. And then we do the same thing for the y's. So 4y is lambda times 2y. Right? And then we have the constraint itself. X squared plus y squared equals 1. All right? And what I like doing, I think it's sort of a nice way to keep track of what you're doing here, is to number these equations, say 1, 2, and 3. All right, so now we're looking for solutions of that system. That's going to be the extreme points of f, subject to this constraint. All right, so what can happen here? We basically just have to do this one by one, case by case. So what we can do is, let's first say, or let's look at equation 1. All right? What can happen here? Well, we could have lambda equals 1. That would satisfy this first equation, because then 2x equals 2x. Or we could have x equals 0, right? Because then it doesn't matter what lambda is, because both sides are 0. Right? So now we break this into our two cases. Right? So what if lambda were 1? What would happen there? Well, if lambda is 1, then let's look at equation 2. What does equation 2 tell us? Well, by equation 2, we must have 4y equals 2y. So what does that mean? That means y has to be 0, right? I mean, you can even solve this algebraically. Subtract the 2y over, you get 2y is 0, so of course y is 0. All right, well, if y is 0, then we have equation 3 coming into play. That's going to say x squared has to be 1. Well, then that means x is plus or minus 1. Right, so we have some candidate points now. Right? So 1, 0 and negative 1, 0 are possible extrema. Okay? Because those are 2 points that satisfy this, right? There's a lambda value, it happens to be 1 here, but those are the 2 x comma y points that satisfy this for some lambda. All right, now we have, in the other case, what if x is 0? Do we get anything here? Well, if x is 0, we can't do anything with equation 2 yet because there's no new information, so we have to use equation 3. Right? In equation 3, if x is 0, then y squared is 1. But just as before, that means y is plus minus 1. All right? Well, now we have to use equation 2. And actually, we get sort of 2 more cases here. Actually, let's bring in a third color. Right? We have the y equals 1 case and the y equals minus 1 case. Right? So if y equals 1, then equation 2, this becomes 4 equals 2 lambda, which says lambda is 2. So there's a solution, right? We can solve for lambda, right? And down here, again, we're going to use equation 2, and that's going to tell us negative 4 is negative 2 lambda. But again, that just means lambda is 2. Right? And again, it means there is a solution. There is a lambda. Right? So what that means then, this tells us that 0, 1 and 0, minus 1 are possible extrema. So actually remember, extrema are exactly the absolute max and the absolute minimum. All right? Relative don't count for that one. Okay. So, what do we do here? Well, now that we have the possible extrema, what we have to do is check. So I like to make a little chart here, and you can do it horizontally or vertically. Because of the board space here, I'll do it horizontally. So we'll have the point, the f value. So the value when we plug the point into the function, and then the type. So whether it's the max, the min, or just nothing. All right? Okay. So we have 4 points. Okay. We have 1, 0. We have minus 1, 0. We have 0, 1. And 0, minus 1. All right. So now we have to take each of these and plug it into f and record the value. So if we plug 1, 0 in up here, we get 1. If we plug negative 1, 0, we also get 1. Plug in 0, 1, and we get 2. And plug in 0, negative 1, and we also get 2. All right? So now what we do is we look at this list of f values. The largest is the maximum. The smallest is the minimum. So we have a tie here for the smallest, so that means they're both minima. So it's a min and a min. And then we have a tie for the largest, so that means they're both maximum, or maxima. Max and max. All right? So since they're both maxima, then, or since they're both the same, in here and here, we have 2 min and 2 max. Right? And that's how these problems go. All that really happens is the system might get more complicated. By the system, I mean this system here of equations. But the method for solving it, like the idea of what to do, is basically the same. You just might have to be a bit more creative when solving it. But once you find these points, you do the same thing every time. Okay? See you in the next video.